Okay, so I guess we'll go ahead and get started here. We got about 31 people on the call. Yeah, Eric's in the other room here at the shop. So it's been a pretty packed last 6 weeks or so, 5 weeks. So Eric got here on, I think, the 2nd of April, same day as Adrian. And Adrian took off last Saturday, about a week ago, 8 days ago or so. And Eric's going to be here for another 7 days, 10 days, something like that. We're just kind of getting to some final stages of completion on some of the projects, which here in a little bit, I'll put Zoom on my phone and then I'll just walk around and Eric can kind of narrate, and Adrian can too, on some of the stuff that we've been working on. Made a lot of progress on some of these projects that have been kind of lying dormant for the last couple of years. We're weeks ahead of progress, and the outcome was beyond anything I think any of us expected. So today is May 6, 2023. So 12:08 p.m. Pacific time. The last call that we did on Zoom was the 15th of April, I think. That one I have not even had time to put that up on YouTube. After Eric leaves, and I'll deal with putting that one up on YouTube and then getting this one up on YouTube. And so what we'll do is, yeah, I'll just make a couple announcements and then see whatever updates Griffin has, Adrian, Eric. Hey, Eric, if you want to take the top of the laptop and pull it towards you a little bit, it'll kind of center you in the video a little bit more.
Okay.
Okay. And yeah, we'll do a little walk around, and then some of the demos that we did do while Adrian was still here, some of it I don't really want to show a video clip of, because it'll be unfair to those coming to the conference who will be able to see it for the first time, meaning the largest flame speaker that's been done in many decades. And it's the first time that much well, actually it's the largest flame speaker, because we were able to get power levels up to a certain point, which has never been applied to the flame speaker. And that all kind of makes sense for anybody who's not really familiar with some of this stuff. And it goes beyond, you know, being something that's entertainment. And I think Adrian has a good take on why we're doing this and kind of what some of the point is to it, which is not just to impress you with the fancy looking spark that makes high fidelity sound, but the refinements that are in the audio modulator bay that we'll kind of go through is really kind of a testimony to, you know, Eric's engineering skill and where we're taking this to a level that I don't think anybody has ever done before. So coming up here in July, I think it's only about eight weeks away, 8.5 weeks or so, is that July 7th through the 10th is sorry, July 5th through the 9th is the Energy Science Technology Conference that's coming up in April. I'm just going to throw up a screenshot here real quick. Just give me a second here and I'll share my screen. So right here at energyscienceconference.com, this is the official website for the conference. It'll be the 11th, or no, actually, I think it'll be the 12th annual Energy Science and Technology Conference. There'll be about 17 presenters. There'll be about 20 presentations, jam-packed for 5 days, nonstop, all day long into the early evening. It's going to be here in Spokane, Washington. About 60% of all the in-person attendee tickets are already sold out. There's plenty of streaming tickets in case you're not able to get to Spokane. But if you scroll down, you'll have all the details here on the date. The location is up here in northwest part of Spokane, and that address is included in the ticket. So let's see, 8 weeks, 3 days, and in the main menu bar, I just edited the schedule, did a little bit of rearranging last night, where we pretty much kind of have it finalized. There might be a couple shorter presentations I might try to weave in through some of these long lunch break times. And Griffin, did you got the message about me moving your presentation time? Does that create any conflicts or problems for you, or is that
No,
okay?
it's perfectly fine.
It's fine. Okay. So normally I try to group all the presentations like non-Tesla stuff together, you know, motors or energizers and engines and other stuff together, all the Tesla high frequency, high voltage stuff together. But to kind of make it work with all the presenters who's going to be able to get there, I had to juggle a few things. So each day may not be perfectly themed one thing or another. But here's the full schedule, 2023 conference schedule. You can scroll down and you can see the bio and the talk description. The only ones that are not on there yet are 2 presentations by Paul Babcock. That's because I don't really want to disclose what we're going to be talking about just yet, but I'll do that pretty soon. And then there's one more presenter with the initials PW, who has a 2-hour presentation on Saturday, the last presentation on Saturday. I'm just waiting for final confirmation that he's going to be making it. Then I'll put up his bio and presentation. And so I think that's enough on the conference. Right now, there is a new booklet that's going to be coming out, the one that Griffin has helped to transcribe. Let me see if I can actually pull that up so you can see the title of that. Let me stop the screen share real quick and go find that. This will be available on Amazon and as a downloadable ebook. Let's see, I think it's kind of titled The 4-Phase Pamphlet. I think I might have it on a different place on this computer. Just give me a second here. Let's see, letting a couple more people into the room here. Looks like Bruce Gavin is joining us as well. The 4-Phase Pamphlet. Okay, actually I have it on the, okay. Okay, this isn't the final version. I got the final version on the computer that Eric is on.
I got the title. Can you hear me?
Yeah, I was just going to pull up the cover of it and show the at least the table of contents, which I think might be edited. But let me Nikola Tesla and polyphase power, is that correct?
Yeah.
Okay, so we're just doing some final edits on this. This particular version is the one before the latest one, where we have to deal with some images and stuff and potential copyright stuff. I think is this table of contents still accurate?
Yeah.
So do you want to kind of give a brief little, you know, couple, maybe a paragraph on each table of contents of what the purpose of this book is and what people are going to get out of it?
Okay, so basically this explains the how and why and what have you of 4-phase power and why Nikola Tesla used it. So the first chapter, so to speak, there, engineering achievements, I give a kind of an engineer's biography of Nikola Tesla. Nothing, you know, romantic or particularly conspiratorial, just the regular, you know, what did he do, who was he, and how does it relate to what we're talking about here. So then next, Goethe and the vision is it just shrunk on me. There we go. It is I really tried to get in the reader's mind what it was that Tesla saw when he had this flash of light vision, and polyphase power appeared to him complete in every aspect. So I go through that just step by step, you know, the sunset and how that related and how, you know, he would have felt in visualizing that and what have you. So, and in this, we developed a basic archetype of 4-phase power. Then the next one is I get into basically the beginnings of a mathematical representation of polyphase power, what its components are and how it relates in its various parts. And then I get into the Fortescue, the 4-phase mathematics, to show in simple terms how the dynamics of 4-phase works. And then getting back into the practical world, I get into the Westinghouse Tesla system, most notably the Chicago World's Fair, because that's where it all began. And I get into actually how the power system worked there. From what little information was available to me, I think I put together a pretty accurate picture of how the switchboard functioned and what the various rotor machines did and the type of distribution systems. It was the biggest power plant in the world at the time. And then it led to Niagara. Now, I was going to write about Niagara, but basically, when you get into the Niagara story, you find that the whole political quagmire of today, actually really nothing new. And this had completely enveloped the whole Niagara project. And it was a miracle that that Westinghouse and Tesla were able to fight all this back and put in a working system rather than something that was completely outrageous, designed by the experts, of course. And J.P. Morgan was the final push. He was not going to let this thing go under with a bunch of buffoonery. So between Westinghouse, Tesla, and J.P. Morgan, we ended up with the power system of today. And in analyzing the original system, it reveals a lot about how and why we have frequencies and voltages that we do today. And that pretty much, and of course, there's a complete references on this. Any statement that I make is backed by something out of a book written by the authorities on the matter. So you can go from this and get right into the thick of it.
Okay. Let's see. I think we've already covered kind of what the presentations are going to be about. I know that Simon Davies over in the UK is helping to work on some of the audio based on the music diagrams and stuff. And
No, I have a question, Aaron. Just for demonstration purposes, that test piece that,
okay.
Can you play that?
So you mean the one where all of the different instruments are
I
playing
want
together?
people to hear that, if possible.
Okay. Yeah, give me a second. Let me pull that out. Okay. Hopefully this will play through the Zoom deal. Okay, before I continue, were you able to hear that on
No.
Zoom? You weren't able to hear that?
No.
Okay, just a second. Okay, I'm going to unplug my headset. Maybe it'll just give me a second here. Were you able to hear that?
I hear it from your room, but I don't hear it on the air.
Okay, let's see. Okay, what I'm going to do is I'm going to put my headset back in.
Can you record it on something while we're talking and then enter it in a more convenient fashion?
I'm going to see if I can just send that to me on my phone, and then I'll just play it over the phone speaker into the mouthpiece.
Aaron, it might be that you need to select a different microphone.
Well, it's showing. Let's see, speaker out.
If on the bottom left where it says mute, you can pull it up and it will say select a microphone. You might have to select the system in order to get system
Same
sound play.
as system. Okay, hold on a second. Can you hear me now?
I can hear you, yes.
Okay, so let me try one more time. Is that working?
No.
Huh. I figured the speaker would at least go into the microphone.
Well,
But
the thing is, I can hear the music in this room. It seems like if you just put that speaker that's playing the music closer to your microphone, or I don't know.
yeah, let me just do what I know will work, which is I'm going to send it to my phone and play it on my phone. You put the phone speaker by my microphone. Oops. Let's see.
I liked it when we had Ampex tape machines and start-stop buttons.
Life got very complicated since
Yeah,
then,
it
Eric.
was so easy.
I know. You just press the play button.
Rest assured, it will work.
But somebody
Even
had
more-
a better idea.
Even more reliable, Griffin, is the ones you have to crank the handle for, because then you don't even have to rely on power.
Okay.
Exactly. I have one of them.
Okay. Okay, are you able to hear that?
No.
Nope.
I
It's
don't
like-
I don't understand how you can hear me right now because I'm speaking to the laptop microphone and I got the speaker on my phone by the microphone on my laptop, but you can hear me speak, but you can't hear the music coming out of the phone.
That's right. Probably yeah.
That absolutely no sense.
No, it's artificial malevolence, so it doesn't like this. That's one of the things about this music is it starts to open up this realm that
Here, one okay, give me a second. I'm gonna play it.
we're kind of using up a lot of time fighting the devil.
Okay, this is the last attempt right here. If I'd have known ahead of time, I would have had this.
Yeah, it just struck me, you know.
Okay, let me try this.
It did it when you had the phone in a certain position.
That's bizarre. That the phone won't play it. That is bizarre.
Yeah, but I can hear the phone in the other room. The computer is deliberately blocking it. Well, at least we just learned something about how our smart technology doesn't like Bach. Isn't that amazing?
Isn't it?
I mean, I can hear it
But you
fine.
you can hear me right now, right?
Yeah,
we can hear you
But you
clearly.
can't
Alan,
hear
yeah.
the music
no,
blasting
it's
over my
blocked it
phone
out.
right now.
It's blocking it out.
We can't hear the music at all.
That's ridiculous. That's beyond ridiculous. Okay,
Let's just,
so
let's
what's
just go back
next?
to Tesla. Well, let's just go back to Tesla technology because that works.
Yeah, right. So okay, so anyway, there's some of the music project going on. Simon's helping us with that. His website is the teslascientific.com, which has all the calculators and stuff. And if you're interested in this kind of thing, you might want to check his website out. But do you have any other updates or anything, Eric? As far as I wish I could have played that, but
Yeah, it's too bad because it was very, very well. The way it was put together was very good, and it really gives the whole layout of the music. It's quite stunning, but we're not allowed. So we at least we learned that. It was. I don't believe it was a waste of time. Now we're starting to see what kind of technology we're dealing with here. It's not a joke, you know. It's kind of horrifying. You're not allowed to play Bach. It's racist. It's amazing.
okay. So Griffin, do you have some updates you want to go over?
Yeah, I have a few.
Okay.
Mainly just a small little slideshow. Let's see, I could probably share my screen. Okay, screen sharing has been disabled for me.
Okay, hold on a second. Let's see. Oh, that's under the security. Okay, and try now.
Okay, can you see my screen?
Yeah.
Okay, let's place this in presentation mode. Okay, so let's move this to the side. Last live call, I was covering the construction of some of the replica Tesla oscillators involving his early high frequency attempts. Now, before here are the two completed units, which was a rather grueling project, especially the object, which is the oil transformer from Tesla's 1892 lecture, that is, which is on the right. Now, because this wooden box must be hermetically sealed to maintain 4 gallons worth of mineral oil, which is quite messy should that go out of hands, that the sealing techniques employed in this involved various natural fibers and resins, including pine pitch, which could be seen coating the very top of it, along with the various porcelain insulators connecting to the primary, secondary, and so forth. So that essentially is the encompassing full embodiment of the oil transformer, which I really haven't seen any modern day replica of. So this will simply be a true first for demonstration purposes. I will be able to bring this with me to the upcoming conference to showcase and likely demonstrate live. And of course, the oscillator to the left is the later refined version of Tesla's high frequency version of the oil transformer, where we have an electromechanical brake on top of the white coil, which is called a charging coil. I won't really get into the principal operation of it, as it will be left for my conference presentation. But in essence, both oscillators are able to produce high frequency currents within the range of 70 kilocycles to 100 kilocycles, which is roughly the range which Tesla was working with, and from what fellow colleagues and myself have deduced are what is adequate for producing certain high frequency effects, especially with single wire tubes. So these will ultimately allow for the production of this phenomenon. And of course, let's see if I could move to the next slide. And encompassing other projects involving the single wire shadow graph tubes and what have you, I have been able to recently acquire a rather expensive but rather unique and vital component to the evacuation system involving homemade vacuum tubes and other single wire lamps. Now, what you are looking at right now is a precision vacuum ion gauge, which has the objective of recording the high vacuum pressures which this vacuum assembly is able to produce. And this will essentially help solve the question of what is the vital vacuum pressure for some of the radiant vacuum tube or radiant tube phenomenon and effects, for what is the vacuum limit of which this occurs, as well as other tubes and what have you. So this has been a long-standing question as to the principal operation of these tubes, but also this assembly allows for the injection of other various gases, including but not limited to argon, neon, krypton, and what have you. So this will ultimately lead to another long research effort going up till the conference, which will likely produce some rather interesting results. And other interesting projects which are also occurring are the replication of radiant matter collectors and accumulators, which Tesla was able to patent near the turn of the century. And the apparatus you're looking at here is essentially a circuit breaker, or what Tesla called a circuit controller. It is not a spark gap, as what the trained eye may observe to be, but is rather a slotted wheel with multiple layers of conducting and non-conducting surfaces, and has the ability to essentially break the circuit in controlled intervals. So this is, of course, actuated by the electric motor in the background and has a variable braking speed of anywhere from 5 brakes per second to all the way up to 200 brakes per second. And this is in collaboration with recent projects involving radiant energy, radiant matter research, as applied to the Tesla shadow graph tube, but also to other interesting electrostatic effects. Let's see, next slide. And this also lends itself to various new receiver developments, which I've been pioneering thus far, involving the radiant matter tube. Now, mind you that this radiant matter tube, not shown in the picture, but in general, poses various and very interesting, unique electrostatic effects, which cannot necessarily be registered with normal equipment. So, of course, this picture is the embodiment of an experimental high vacuum receiver, which makes use of a variable plasma, which would be set up in the vacuum tube shown on the left, which I was able to develop, and essentially is actuated by a variable magnetic field consisting of a low frequency pancake coil shown on the right. And when these objects are placed inside each other, that you're able to develop a very unique sensitive receiver, which is able to be actuated by radiant streams of electrostatic force from what I've been able to observe thus far. So this is, of course, a very tentative design for a receiver, but of course, it will likely and hopefully manifest into a rather sensitive, even more sensitive embodiment of this object. And this is the tube that I have shown in the previous slide up close, where we have two plates imposed in a high vacuum, but such a vacuum to allow the readily formation of plasma formation with water vapor and other contaminants found within the vacuum, which would otherwise be required to be dispelled in the vacuum, but in this case are necessary for this receiver or this vacuum tube to operate correctly. So that's one laborious project which has been underway, but of course is still needing vast amounts of research as we speak. And of course, with the other projects, multitude of projects that is, which are existing at the present, I will be going with some other colleagues of mine down to Tonopah with Eric to work on various telluric research. And as shown in a previous live call, I was able to develop a scale model replica of the Alexanderson system or coil for telluric research. Now, a larger form of this coil will be constructed. And here we could see a rough sketch of the insulator supports, which will be placed on this coil to facilitate low frequency operation around 60 kilocycles, give or take, which coincides with a WWV beacon for furthering research. Now, this is, of course, the initial step for the construction of this coil, but my fellow colleague Hakasays will endeavor upon the construction of this coil, which is roughly around 2 feet by 2 feet in geometry. And of course, these insulator supports consists of HDPE plastic, which is a form of polyethylene, and extend themselves to around 2.5 inches in length. Now, of course, this is a very, highly tentative design, so this insulator construction could be variable, but nonetheless, this is the rudimentary outline of what is going to be constructed. And that essentially is consists of the projects being constructed thus far. So I'll hand it over to Adrian.
Thanks, Griffin. Aaron, it might be a good time to take that walk around of the lab, because I mean, much of what we're going to talk about, I think, is what we've been doing over the last while. So it'd be useful to see those things first, I think. Eric,
Okay.
Unless you wanted to add something first.
No, that's kind of where I'm at now. I mean, I just took a break of 5 months with my face in a panel, stripping and soldering wires.
I know, I watched you do it. I soldered quite a few myself too.
Yeah.
So yeah, we can do a walkthrough, and then I can pull up some pictures of at least what the
And then
flame
we can
speaker
discuss
looks
it.
like. And
And then we can discuss it in detail,
Sure.
Aaron.
okay, so you want to come in here, Eric, and then you can kind of narrate as we're kind of going around, and Adrian, you can give comment on some of the
Sure,
some of the
will
stuff
do.
that's going on with the hybrid system.
Yep.
Okay, hold on a second. Let me.
Aaron, we can't hear you. You're on mute with your mobile.
That's good now.
Yep, it's good now.
Okay, flip the camera around. Okay.
So I might as well start here. This is fresh.
Okay.
So this is what's going on right now. The medium voltage rectifier. So it kind of grows as it goes. So I'm working my way out of one part now and the rest of it. So this one's actually fairly simple compared to most of the stuff. This is the parts here. So we have the bias rectifier and the screen grid rectifier, filter chokes. This is the bias transformer. This is the screen transformer. And then this is what holds all the bleeder resistors and high voltage diodes and all that kind of stuff. So it's evolving right now, and this is half of it. The other half is over here. Actually, let me bring it in here. What's it look like? Everything's pretty modular right now. So this is the control panel for the medium voltage rectifier, the filament voltage for the PA tubes, and the plate voltage control and all of that. So basically, before we just had it kind of cobbed together to turn the dangerous high voltage on and off, but now there'll be the appropriate switches and lights, and even when the thing's basically turned off, there'll still be a light to indicate that it's active and plugged in. So this thing mates to what I previously showed you. And this is the back of this. This is done, thank God. When you first look at it, you just go, how am I going to get find out that you planned exactly, even though you didn't know the exact number of terminals necessary for each wire. Kind of just all works out by itself, which is good. So then that plugs in here. And then once it's in, then the big effort why Adrian was here was the this very complex network and rectifier system here. Let me get the.
Do you want to explain what this whole thing is here in the bottom of the RF rack?
So basically, this is a thing that develops a 2,400 or 4,800 volts DC, and also the network allows the amplitude modulation power to enter the DC at this point. So basically, there's a network down on the bottom. You can see the capacitors. There's big coils. There's one of the big coils here. It's the inductors, about 100 pounds of them, and that's got a high pass filter to let the audio in and the low pass filter to let the DC in, and that way the two don't interfere with each other. And this is kind of the main power here. It's distribution right now. The high voltage resistors for the voltmeter and protection relays, that'll go on here. And this thing was it was really a workout to get all this stuff in here. So Adrian basically, he picked up where I left off and went through and checked everything and made sure that all the terminals were right and all that. And then we plugged it in and nothing blew up. So these are the main power transformers here. And then in here goes the pair of high power tetrodes that power supply feeds. So the medium voltage rectifier, which I showed on the bench, is that supplies all the auxiliary voltages to this, screen voltage and grid voltages. Then there's another unit.
And to give a little context between these two units, this audio modulator bay, and this is the RF one, which Adrian Eric got this 100% running and doing exactly what it's supposed to. And what Eric is showing is the radio frequency side, and he's getting as much done as possible while he's up here at the shop.
So that the rectifier and control panel will probably be the most difficult, but then also the grid control panel that's basically empty right now, but the front's cut. So the grid drive unit is over here. That takes the power from the exciter and drives the grid to the power amplifier tubes. This was excised from a World War II aircraft transmitter. Just took a piece of it out and put it in another package. So that'll be in there. And then also the various grid control, bias voltage, cathode modulation, screen grid modulation, all that stuff enters through there. And these are the chassis that go in there. So this is the high-speed relay. No, this is the vacuum tube chassis. This is the high-speed relay chassis. So these high-speed relays, let me pull one out of the bucket here. These things will switch up to 200 times a second. And they're good for about 100 milliamps each. So what this does is it parallels 6 of them to key the cathodes of the tubes. These things aren't particularly easy to find. So that all the wiring for that, you have to have equalizing resistors so that one relay contact doesn't take the first hit. And then you have to have the anti-EMF capacitors that no high voltage inductive open circuits will burn the contacts up either, because these things are not replaceable. You can't afford to screw them up. This is the grid voltage regulator and also the audio preamplifier to feed back into the cathodes of the tubes so that the size of the flame varies with the volume of the music. So when there's no music, the flame completely vanishes. That way it operates more efficiently. And also feedback will come through that point to make the modulation more linear, because the flame kind of distorts the amplitude versus power situation. So this is not done. We don't expect to get that done this time around, but what we did in order to bypass that is Adrian had kind of experimental unit and of the self-oscillating variety, and it was difficult to get this thing to work because you cannot 100% amplitude modulate an oscillator because it keeps knocking it off frequency. And so, but we get about 30–40% modulation, which produced a loud enough flame off the discharge point. Power about the same as what will come out of the unit in the rack, about 1,502 kilowatts.
And this is the unit Adrian had at last year's conference with the golden ratio discharge experiments. And so kind of what happened is that since there wasn't time to 100% complete this RF bay for the conference, because there's a whole other unit here that is pretty complex. It's going to take a long time.
So right now the Collins will replace that.
Yeah, the Collins will replace that. And using Adrian's generator with the high voltage supply here, Eric and Adrian came up with the idea to basically hybridize it and use this with what Adrian brought, because that's the only way that we'll be able to have something at the next level for the conference. And then as time permits after that, then we'll get back to the RF project and do it as we can.
I'll add some more, Aaron, if you like.
Yeah, go for it.
Okay, so we just take a look at what the hybrid system actually is. So what Eric was showing us, all the units come from the RF bay, and the bit that we have completed and we tested was actually the high voltage, the high voltage DC supply at the bottom. That's quite a powerful unit. So that's 2400 or 4800 volts at about it's about a kilowatt total output power. Not something you want to get too close to when it's on. So we decided to connect that to, that unit that I used at the conference last year, that's quite a flexible up to 2.5 kilowatt double tube unit. It uses a pair of 3500 ZGs in there, and it is all self-contained. So it is a self-contained unit which also has tuning. It has all of the bias control in there, and you can actually configure it as power oscillator, a linear amplifier, or a number of other different arrangements. I intended it originally as a generator all in one box. Essentially, that was what I could fit into my case to bring over to the conference, and I intended it for a whole range of different experiments, which is now turning out the case. It's quite good that we could actually plug it onto the high voltage bay, which supplies the DC. I have another power unit that I use it there, which I used for the conference last year. I'm going to use that for the conference this year. So we're using this generator now as a power oscillator, as Eric said, and the audio frequency from the audio bay is combined in that network in the high voltage unit, and then the final output of that feeds the generator. So we have an amplitude modulated high voltage going to the generator, and then the generator then tunes that to the coils. Now the coils themselves, those are coils we also made in the last couple of weeks. So we took the model of the coils that I used for the golden ratio discharge last year. That's it. Yes, if you just zoom in on one of them. So that's not the same coil as I used last year. We actually made those coils again. So those coils are designed, they are not designed with anything golden ratio in mind. They don't have any golden ratio proportions. It's basically a 5-to-1 regular Tesla coil. It's designed for high voltage inversion, hence there's quite a lot of turns, and it's tall and narrow. It is designed though with a specific spacing of the inner conductor to the outer silicone coating of the wire. So that puts the wire spacing at a certain distance, and that means its quarter wavelength resonant frequency falls around about 3 megacycles, which is important for the not only for the generator, but also for the kind of discharges that we're going to be demonstrating and working with. The primary unit is the one that, so the primary coil there is the one that I used last year at the conference. It also, you'll note at the bottom, has a small feedback coil that allows feedback to go back to the generator. This is a self oscillator, so and that's particularly important when we're looking at some of the more real work of nature type phenomena, like for example the golden ratio discharge. I'll be going into a lot more detail about this at the conference. Now, the other thing also is that we did is that when you just run a quarter wave Tesla coil like this, or a configuration which is in quarter wave mode. So in other words, what I mean by that, if you can just move out Aaron slightly on the coil so we can see the whole coil. Now, basically, you've got a resonator there where you have the primary coil is at one end, is at the bottom end. So we treat that, for example, as the points of 0 voltage and maximum current. At the other end of the coil, at the top end or the hot end of the secondary coil, we essentially are treating that point as a node of maximum voltage. So if we look at the distribution across that coil, just in broad sense, we would call that a quarter wave coil. It's being driven in a quarter wave configuration. So in other words, one end is a low impedance and the other end is a high impedance. If, of course, we were to move that primary into the middle of that coil, then we would be looking at driving that coil as a half wave resonator. So then we would have, that's right, if we slide it down, so that's now driving it in half wave mode. So we have low impedance point with the primary in the middle, and we have 2 high impedance points at each ends of the coil. So if you just slide that back again, Aaron. So when we're driving in quarter wave mode like that, obviously, and we are driving at very high power. So in other words, that generator is capable of putting out up to 2.5 kilowatts. We had it running up to about 2 kilowatts over the last few weeks. You are essentially producing an enormous amount of broadcast RF. So as Eric said, you know, he's got very sensitive receiving equipment at that frequency in his car. He could have gone anywhere in Spokane, probably anywhere in Washington, and picked up that thing. So obviously what we have to do is, well, we don't want to do that really. It plays havoc, and it's also, we're not supposed to be doing that on the broadcast bands. So we also found that a lot of that RF was also going back into, say, the audio bay. So there was a lot of pickup between the two. So it was necessary to isolate all of that. So that's why you see it all mounted on this large table. We had to build a new experimental table on wheels here with an aluminium top surface. And instead of connecting the bottom end of the quarter wave resonator to an RF ground, or typically to the line ground as you would just run it normally at home, we connect the bottom end of that coil to the aluminium top surface of the table. Now, that has a significant advantage, because now, as a quarter wave resonator, the flux lines that come off of that coil, instead of being broadcast off of the coil, they're basically now being contained in the cavity between the table and the Tesla coil. So if we imagine the Tesla coil here above the plane, and we imagine flux lines, essentially we're forming a cavity between that coil and the top surface of the table, and that makes an enormous difference to the amount of broadcast energy. So much so, for example, that we could take a ordinary fluorescent light bulb and we could touch it down to the chassis of the audio bay, and without grounding to the table, that thing is lighting quite brightly. So in other words, there's a lot of RF energy coming through the earth and ground system, enough to light a light bulb directly off of the chassis of the RF rack of those large modular racks. With the top surface aluminium and properly connected, that bulb was almost completely out. So there was hardly any RF energy at all going into the system. And that also means it's not being broadcast either. So that's a big step forward, and it's a very important thing to consider when running Tesla coils in quarter wave mode, and something that allows quite high power experiments without producing lots of RF noise. The other way to do it, which we also experimented, Aaron, if you could show that there's a second coil, which you are doing, that is a counterpoise coil. So in other words, if we were to connect the two bottom ends of those coils, we essentially have a quarter wave counterpoise. So now in effect we have a balanced system, or as balanced as it can be, given that the primary is actually driving the bottom end of one of those quarter wave coils. I mean, the most ideal situation, we would essentially have one long coil with the primary in the middle to get a completely balanced system. But the counterpoise has several advantages, and it doesn't, if you position it correctly, it doesn't make a massive change to the operation frequency, which is a very interesting consideration with a counterpoise, because you are physically electrically connecting two quarter wave coils, which means there's going to be a beat frequency developed, there's going to be frequency splitting, involved there, and it means you are introducing additional modes into the characteristics of the coils. So you have two sets of series modes, two sets of parallel modes, and they are interacting with each other. And if it's properly balanced, they don't impact on each other. They actually cancel each other. And all of that flux is contained between the two coils. So that's one advantage. Now, we tried that as well in order to see if we could get the RF, radiated RF down even lower. Didn't seem to make much of a difference. The table, the aluminium table adequately captured that flux in creating cavity between the coil and the table. Undoubtedly, with the counterpoise, it was slightly better, but there was nothing that we could actually measure in terms of difference in terms of the radiated energy from that system. Now, the other advantage of the counterpoise is, Aaron, if you could turn it round so that it's in parallel with the first coil.
I mean, 90 degrees?
180 degrees.
Oh.
So the advantage of that system now is we have two energized coils working in push-pull with each other. So effectively we create now a cosmic induction generator cavity. So, and quite an intense one. So in other words, if we remember the experiments or the demonstrations that were done last year with the special Tesla bulbs, where they were put between two coils and generated all kinds of special effects in the plasma, that was a starting point. Yes, those coils there, that was the starting point to the cosmic induction generator experiments. So in other words, what happens in those space and counter space scenarios with the magnetic and dielectric induction fields, both acting with each other and also acting against each other and creating spaces of induction field nulls, and where they support each other and where they cancel each other. So all of those special relationships between those two induction fields. Now, with this system run like that, we've got the capability of making that much more intense. So in other words, to really get those, to drive those two counterpoise coils hard, so they are basically reinforcing each other, or they are basically balanced and they are cancelling each other. So this hybrid system opens up quite a large set of possible experiments that we can do and we can demonstrate at quite high power. So before, the flame speaker was up to 100 watts using the Collins. Now we have the capability, and prior to the RF bay being ready, now we have the capability to go up to 2 kilowatts of power. And we also have the facility for amplitude modulate that as well. So the first result of this, obviously we're going to do a lot more at the conference. I'll be demonstrating it, but it was successful in generating the burning bush, which is basically what the kind of discharge that you get when you run a Tesla coil at reasonably high frequency, so in the region of about 1 to 5 megacycles. If your high voltage supply is producing a constant DC, that is, it doesn't have an envelope, doesn't have some kind of modulation envelope, or it's not keyed, or it's not chopped or switched, then you're going to get what's called the burning bush, which is a form of plasma flare. So it's quite a high power, quite intense burning area where you would normally get a discharge, basically a form of plasma flame. And that plasma flame, when we ran it at the full 4,800 volts, was around about 4 inches, high, a 4-inch high plasma flame. And with the 2,400 volts, it was about 2 inches up to, which would make sense. It was about half. since the size of the flame is very much related to the size of the voltage that's applied to the primary, or the intensity coming off of the HT, or the high voltage supply, then on top of that, then when the cathode keying is ready, or when we modulate it, then we're also able to start accessing different properties of the flame. So the burning bush is the starting point, and we already noticed that by having some modulation, some amplitude modulation, and some switching, that the form of that discharge starts to change. So it produces a range of different demonstration effects, and it kind of brings me to a point that I wanted to emphasize. Aaron did allude to this earlier, but to a very important point around the underlying reasons for doing these experiments. And I think this is what is often misunderstood about, you know, there is so much work or so much time spent on YouTube, for example, making Tesla coils with large discharges, and for entertainment, for presentation, or just to see how big a spark you can make. And in a way, it's very easy to pass off a Tesla coil as, you know, well, it just produces a lot of sparks and a lot of discharges, and it's not useful to do that. Well, we have to take a stage further and look at a Tesla coil as a very advanced electricity laboratory. Most of the principles and processes going on in a Tesla coil are not that well understood, if at all. The type of modes, the relationships between the magnetic and the dielectric induction field going on at different frequencies, different qualities of vibration with modulation, produce a very wide range of special electricity effects, which some of those effects are not easily explained. For example, I mean, take the golden ratio discharge, for example. When you start looking in detail in that discharge, and I will be showing some very detailed slow motion video, ultra slow motion video of the golden ratio discharge and how it forms, and the symmetry, and the mathematical expansion that it follows, and all of these kinds of things, you realize that you are dealing with something much more fundamental than just dealing with what you would call a spark or a discharge. So see the discharge from a Tesla coil as a visual representation of the final endpoint of the relationship of the magnetic and dielectric induction fields that are going on there. And hence it becomes a sophisticated laboratory. As we adjust the parameters of the coil, as we use combine the coils in different ways with the counterpoise, with the cosmic induction generator, the flame speaker, the golden ratio discharge, all of these different experiments are showing fundamental principles of electricity if we choose to look at it and work with it in that way. And I think that's what makes this kind of research very important. And not many people are doing it in this kind of way. So in other words, when we look at the flame speaker, yes, we can play music with it, but the type of response, the geometrical form that it creates, how it is different depending on the type of music, what happens when you start to modulate it, when it key it, when you switch it very at high speed with an SCR, for example. There are so many factors here which change the discharge, and that's what I think really needs to be understood about this. This is fundamental research regarding, in my mind, essentially the fundamental principles of nature. If you can get a discharge like the golden ratio discharge from a Tesla coil, then you are starting to probe some of those underlying principles, which are the very foundation of the real work of nature. And really, I'd like to, the conference is going to be a lot more about this kind of fundamental research from all of us, all the work that we're doing, what Griffin is doing with his Tesla bulbs and the radiant bulbs and stuff like that is most fundamental research. And it's quite groundbreaking. in that respect. So that's really my take. I mean, there is a lot more. There's a lot deeper take on that I haven't even started talking about. Some of the natural and metaphysical processes that might be going on in the principles of electricity, but that is something that we are going to be getting into in the conference. So, as Aaron said at the beginning of this, the 5 weeks that we spent together in the United States working together were really quite a fundamental step forward. Not only with the technology and with the experiments, but also as working together as a team. That might sound straightforward, but really, I think, I mean, Aaron, do say what you think as well, but really, when I look at what we accomplished, none of us could have done that individually. And it's that kind of collective intent of actually working together, which is going to really take this research on very far. And, you know, just finally to say that I think we are in striking distance, or starting to be in striking distance, of actually really getting down to some of the most fundamental underlying principles in terms of electricity, Tesla coils, and how all of that actually works together. And if we can do that, and we can harness some of that, then I think we will have started to do what Tesla originally said. That profound statement that he made, that you know, there will come a time when man will learn to attach their apparatus and experiments to the very will work of nature. I think he knew how to do some of that, and he did some of that. And we are really just rediscovering that process of how to do that. So that was, for me, really a summary of what we did in the last 5 weeks. And if we can do that for 5 weeks, then if we pool our efforts, focus our resources and things like that, then we really should be able to make some quite stunning step forwards in the future. I think that was that was the long answer, Aaron.
Okay. Let's see. Simon said that he could actually play the audio clip if we want to give that a try. And then, but before, do you want to mention the significance of that piece of music, Eric, and how that kind of fits into the whole category, you know, topic of Tesla and the 4-phase mathematics? And
well, it's a very 4-phase piece of music in the way that it's constructed, and it's simple. I mean, it's not ultimately simple. It's, you know, Bach didn't really write simple music, but it's easy to understand. It develops rapidly, and it just seemed to be the perfect piece of music. It's not flamboyant, or, you know, doesn't shake the church. So that's what I decided to work on. And then, you know, I'm learning as I go with this. It's all experimental. So once I got the stuff transcribed, then the musical notation's hard to follow because it's a shorthand. So I basically turned it into more of an oscilloscope type representation to see the patterns. So I'll go through all that and point out, you know, the interesting ways that the music all progresses, because basically Bach's music all starts from the archetype, which is the first basic element, and it starts in the beginning of the music. That's characteristic of a fugue, and that element is repeated over and over again in different phases, and evolves and interacts, and that simple little 4 notes can just turn into a fantastic dynamic, in this case being a 4-phase dynamic. Now, obviously, the Bach and the music goes way beyond any kind of polyphase systems or specific Fortescue mathematics, but at any rate, it does provide that other end, that the music mirrors the Tesla 4-phase system. That's kind of why I'm bringing the two of them together. And right now, my interest is much more in the music than any technology. In fact, I don't have any further interest in technology whatsoever. But I am pursuing the the Tesla transmission system. Some experiments have been done recently with Steve McGreevy and Steve Young in Owens Valley by Lone Pine, which is a massive earthquake fault and a water sump for the Owens River. And they got some stunning transmission results. I've yet to see, actually what happened, but they called here on the phone. And when I get back that neighborhood all see what's going on. And then the importance of this whole zero sequence current thing causing interference when people are using quarter wave coils without a counterpoise, or, you know, push pull like I've been doing all along to eliminate that problem. It presented itself, you know, rather strikingly, the way it just lit the wiring up in this building. And even with the spark on the end. Now, if there wasn't a spark on the end, if somehow you could hold that back so it did not essentially short circuit the coil, that 1 or 2 kilowatt level probably would have burned out all the electronics in the building. So this really isn't anything to be fooling around with. It's what irritates me about this YouTube stuff, you know, is everybody's trying to make a bigger fire and what have, but they have no regard what they're pumping back into the power system. And, you know, I may be screwing somebody's stuff up further down the line. This is what I had to hash out with the MWO design. The original MWO design could be classified as nothing other than an electromagnetic terrorist tool. And in today's paranoid environment, you know, that can get you in big trouble. It's the same thing, you know, if you're transmitting on, let's say, 3.3 megacycles, well, I can tell you from experience at 3.3 megacycles, there's certain international military operations that go on in those frequencies. And you start jamming that stuff, you're going to have unfriendly visitors. So basically farting around in irresponsibility with these forces and devices could actually get everybody in trouble and get this stuff shut down. Of course, no one's going to pay attention to that. But at any rate, I insist upon it in my environment. And it presented itself very forcibly here, how much RF came back in. And in the fooling around and what have you, is I feel, I was never absolutely certain, but I think we've adequately demonstrated that the open loop Helmholtz current is a reality. It's a true zero sequence current. It has no phases at all. It's no plus or minus. It's just simply one pole. It's monopolar, and that current, monopolar current, just goes straight out from the coil. And Helmholtz and Tesla actually discussed the matter together. And Helmholtz told Tesla that if he could build the right transformer, that this would work. This is completely against the Maxwell-Einstein concept of electricity, as open loop currents cannot possibly exist. That's one of the disadvantages of Heaviside's work, is he railed in the same direction. But unfortunately, the Heaviside for Helmholtz, Heinrich Hertz, he died at a very early age, around 33, I believe, or somewhere around there, 35, and was not able to carry any of this further. But that's basically what the communications end of this is moving. It's moving along those lines. Is can we get that current to transmit, you know, through the earth from one point to another under whatever circumstances? So that's what we're still striving for. So when Griffin and I get together in Tonopah, we're going to complete the telluric test platform. The poles are up, the tank grounding's all in and all that. So we just have to build the deck, and he's bringing the Alexanderson coil, and that'll bring some interesting results in. So I think that's all I have to say on the matter right now.
Let's see, Simon, if you can hear me, if you want to try to play the song, you're unmuted, so it should come through if you're able to patch it through. Okay, that worked.
So that's basically that segment of Bach's music is what I'm going to analyze from the four-phase standpoint and whatever I learn out of the process. And then I'll play the entire piece of music. The recording that I have is an excellent one. And the beginning part of that presentation is I'll repeat some of the stuff that I did very early on of how this musical scale actually came about as a result of the efforts of Pythagoras and Plato, and just kind of give a background of, why there's so many black keys and why there's so many white keys, and why, there's all these musical scales that we don't use anymore, and the fact that A is supposed to be 4/26 2/3. The Pythagorean music is based on a pair of coordinate systems where one is rational and the other one is irrational. So the C is 256, but the A is 46 2/3, which basically, is the sixes keep on going on forever. It's not capable of numerical expression. It has to be expressed as a ratio of 2 to 3. So, and I've worked that out a lot. So I'm going to get into all that on kind of just a precursory level. I'm not going to get into anything in depth. Most of the material I'm using out of either my presentation, the musical seismograph, or the power of the ether is related to music and electricity, where I got into more depths of this. And there's a number of energetic form. I don't know if that stuff exists anymore. I wrote a number of articles based on a book called The Music of the Spheres by, not the physics fraud by Murchie, but the real book by Jameson, I believe is his name, or Jamies or something, which really reawakened me into how all this music came about, and how there's basically, after the death of Bach, most of the finer components of music all just completely evaporated. So that will pretty much fill in the 90 minutes, and it'll end with a piece of Bach music.
That's the book you're talking about, Eric. Jamie James.
Yeah. Very good book.
And let's see. One of these images I showed is not the actual piece of music you heard, but this is along the lines of what what Eric is talking about, the oscilloscope type of diagrams.
Go to the image just before that one, if you can.
That one?
All I have is the music of spheres.
Really? What do you see, Adrian?
Yeah, I can see your. Oh, I could see your screen. It's gone now.
There it is.
Yeah. I can see the Bach. Yep.
Yeah. So this quantifies it pretty definitely, where the musical notes are hard to interpret. So this is basically what you would see on like an oscilloscope spectrum analyzer combination. So you can really plainly see the dynamics of the music, but then when you hear it, it opens up a whole nother dynamic, because then there's patterns that you're sensible to. I'm hoping maybe somewhere along the line, I might be dreaming of this, but if we can get the what it appears here on the paper to each note becomes highlighted as the music plays, that would really be interesting, but that might just be too complicated. But I don't know, there's some pretty interesting stuff going on with what you can do with computer programs. So maybe we might be able to do that, but first things first.
Okay. And, I do want to mention that, let's see. Can you hear this okay?
Yep.
It's fine.
It's working okay. Do this real quick. So now with Eric, there is an organization, EPD Laboratories Inc., which is a 501c3 nonprofit. I want to pull up Eric's website right here, because as far as the research with Eric goes, and the nonprofit, it's all basically surviving on donations. Let me pull the website up here. Okay, so ericpdollard.com. This is the official website for EPD Laboratories Inc. And there's a donate link right here. It used to be in the column, so you can find it easily in the main menu bar. And here's a PayPal donate link. This is how most people support EPD Laboratories Inc. with donations. And there's also a check or money order address here in Spokane, Washington. And when I get those checks or money orders, I just endorse them and send them down to the bank account. But if there's anything that anybody is able to donate, a lot of the EPD Labs expenses just went up. The building insurance outright doubled. Actually, it went up about 210, 215% compared to what it used to be. And that's kind of a hard hit for the amount of finances available. So anything helps. You can, spread the word that EPD Laboratories Inc. does need some donations, and, it goes to exactly furthering this type of work. And, I'm sure here in about 3 weeks, when Eric is down in Tonopah with possibly Griffin at that time and a few others, you're going to be seeing a lot of the stuff going on down there. As far as my own involvement up here of what's been going on at the shop all throughout April and May, there's been a substantial amount of money that I've paid out of my pocket to support all the efforts and everything going on here. I'm not really asking for donations on a normal basis, but the amount of money expenditures that happened is it adds up to a small fortune. And if anybody, because I'm putting money out of my pocket to do a lot of this stuff, and basically the public is kind of the recipient to a lot of the information and results and everything that kind of happens. It's not completely fair to me. I should be charging everybody, by the hour to have a peek at what we're doing and doing this kind of thing, but I don't. And so if anybody wants to donate any funds to kind of make it a little bit fair for myself, shop at emediapress.com on PayPal is my main business PayPal address. And if anybody wants to help support that as well, it makes it easier to keep doing this and basically just handing out this information for free, because it's not cheap. It's cost a fortune. You're talking about those 2 racks there. That's approaching, $75,000, $80,000 out of my pocket to make that happen. That's not in parts. That's for motel room for Eric and travel and lodging and meals and parts and overhead and all this kind of stuff. And that's just one thing that I've, put money out of my pocket to do the best I can to make that kind of thing happen. So it adds up, and any kind of support that anybody wants to help pitch in for that, since everybody is, able to get their hands on what we're learning here, would be appreciated. Again, the conference is coming up in July. It's about 60% of the tickets are sold out for in person. And then, so that'll be energyscienceconference.com, and the tickets, it'll forward you to emediapress.com, where you can purchase either the in-person tickets or the live streaming tickets. So that's coming up in 8 weeks and 3 days. So that's gonna come pretty fast. It's a lot of work, a lot of stress putting these conferences together and running the businesses and doing, working hands-on, working on all these projects and stuff. It's not an easy task, but it's moving forward. It is going to be an incredible conference. There's a lot of amazing presenters and presentations, and I think we can probably, Eric, you want to go ahead and just open up for questions if anybody has it. I haven't. It's kind of hard to kind of keep track of what people are posting in the chat while doing this, but if anybody has a question, down at the bottom of your screen, I think it's under reactions. You can do the little up arrow, and you can raise your hand, and then we can unmute you. You can introduce yourself, where you're from, and just say who you're addressing your question to. Constantine, okay, just give me a second here. Yeah, go for it.
Hi, can you hear me?
I can't, yeah, if you can speak up just a little bit louder, go ahead.
Okay, so I have a quick question for Eric, if possible.
Can you hear
So
him, Eric?
Yeah, I can hear okay.
Okay, so I'm Konstantin from Russia, Western Russia, 31 years old, region of Kaliningrad. And, if we can just go back to Peter Lindemann circuit of coal electricity that he describes to us. So how can we achieve like free energy from capacitor discharge, disruptive discharge? Let's say if we, like he explains, if we discharge a capacitor through a spark gap and let's say vacuum triode, okay, so can we just feed a square wave to the triode to make and break the circuit to make the impulses? Can you just comment on that, please?
Well, you can't really get any free electricity out of any of that.
Why not?
Well, it doesn't work.
What essentially, if to add on to that, when a disruptive discharge circuit like you're talking about, when a capacitor is discharged, what happens is that there's a transient impulse, which is essentially created. That isn't really any free energy or any observable free energy, which is being created. It's simply the expenditure of the stored quantity, which is within the condenser. There's nothing really being extraordinarily that's being generated.
Mm-hmm.
I would
Well-
just add on to what Griffin was sharing as well. I think it's a very important question in this field to ask. What, if anything, is for free? There's nothing free in this world. That includes electricity.
Well, what about Edwin Gray circuit? Didn't he
Well,
get?
all of that stuff basically is just, it's all run its course. There is no free energy. It was kind of, the whole thing was really just a big vaudeville act. I wasted a lot of my own time on it. It didn't pan out. Most of the players in this free energy thing they're all vaudeville actors. So the free energy's run its course. There is no free energy. If after decades and decades and decades and millions of dollars poured into this stuff and not one thing came out of it other than a bunch of hype. So we're pretty much all done with free energy.
Well, that's very
I'm-
surprising.
I'm very much involved in it myself, and I have a different opinion from Eric, Griffin, and Adrian. But it's also a little bit off topic for this call, so I don't want to go into it, but I will show you a couple photographs here real quick. Actually, maybe just one. So while Adrian was still here in Spokane, Mark McKay, who is the leading authority on the history of all that, did bring over this little scale model that was from Gray, which was used as a marketing device to show basically what the final motor would look like. This is a very rare piece of history right here, and the detail is incredible. The model is absolutely beautiful. But on energeticforum.com, I've put quite a bit of my own opinions on there, and if you look on my YouTube channel, you can see some videos that I put up giving a comparison between the so-called Gray conversion element tube, the CET, or the so-called Gray tube, and how you're clashing two different high voltage, or a high voltage positive potential into a low voltage potential positive that both have common neutrals. And when the low voltage shuts off, that high voltage has nowhere to go, that discharge has nowhere to go but over to the grids that the inductor is connected to, ionizing that gap, allowing a low voltage high current source to jump over a gap that is normally not thought to be possible. It's 100% identical in the sequence of the switching process as what my plasma ignition is. And I've given all my opinion and all that on my YouTube channel, youtube.com/Aaron Murakami. And you can see the comparison between the Gray circuit with the tube and my plasma ignition. Now, as far as free energy claims, there are over many decades showing that violations of thermodynamics happen all the time when you have these sharp gradients. When you have that sharp impulse, is that it's polarizing the ether at those 2 points, which allows more to come into the circuit to add more so-called electromotive force into that circuit at those 2 points of those sharp gradients, which is above and beyond what you're supplying from your source dipole. And that's pretty much all I want to say about it at this point. Because again, it's a little bit off topic, but that's my 2 cents at this moment.
Okay.
Konstantin, I would also add another point in there. It's because it's important in this field. Is if we look at, that's why I mentioned it earlier. It's not that there aren't very miraculous phenomena and very fundamental principles to be discovered. There are, which is why it was so important what Tesla said. I mean, Tesla was a real pioneer in this area, as were others as well. But Tesla particularly stands out in the area of electricity and energy, where he said about learning to attach our experiments and apparatus to the very will work of nature.
Yeah.
Now, that's a very profound statement, that, if one considers it even a little bit. What is being asked there goes far beyond what we're currently considering with the apparatus that we just build on the bench. So there is a whole mystery to be unfolded here, and that we don't know about. So there is a lot of work to be done in here, and we are really only at the beginning of this research. And in that respect, all of these experiments, everything that we're explaining, the demonstrations, flame speaker, golden ratio discharge, the telluric work, the work that Griffin's doing with the radiant bulbs, everything like that, they are all, if you like, they're all experiments leading to a more or we hope leading to a more fundamental understanding of the natural order and the natural processes going on. And it's those that I think are things there to be discovered, of which Tesla had done more than most in being able to do that. So in the way that we answered you, it's not that we're saying there is a whole mystery out there to discover in terms of electricity and energy, but in the way that it's put over, as in terms of, you just build this thing on the bench, and if you do it right, you're going to get some free energy. We're just simply talking from experience. It doesn't seem to happen that way in our experience. That's what I would add for you.
And
Okay.
Konstantin, I just want to show you something real quick here. You can go to YouTube, and then
Yeah.
you can see, hold on, it's loading up right now. You can see this video right here from 2015, gray tube compared to the plasma ignition. And you'll look at the basic principle of that switching method. And then on my channel, you can see different replications of, I actually used the plasma ignition method to run an inductor for a pulsed plasma discharge motor. And I got multiple videos on that, so you can kind of see my school of thought on that. And other than those experiments, I don't know anybody else in the world that is running a pulsed motor like that based on the discharge of colliding a high voltage into a low voltage. Okay, just like in the gray tube, but I think that's probably about all we need to go into on that subject. Unless you have a different question relative to kind of the walkthrough on what we have been talking about on this call, then maybe we can take some other questions.
Well, maybe not really about today's topic, but didn't Tesla have a power supply for his car, which he made in 1929, 1930, which used some vacuum tubes from a store, conventional tubes, that he powered a car, which Jerry Vassiladis talks about in his book. So
there's a lot of propaganda about that story.
Have you ever met anybody that made one, Konstantin?
Unfortunately not. I've
No,
only-
neither have we.
But nobody even knows what it was supposed to be. There's just
Well,
a story about it.
Exactly. Well, exactly. But this I think is an important area. There is a mythology which is so big surrounding this area in this field. There are things to, that's why I was trying to say there are things to be discovered. But one of the first jobs in being a responsible researcher in the area of what I call basically the new science is in looking at, is trying to basically peel away what is basically myth and mythology and hearsay, and actually what is the real experimental work or the real discovery that needs to be made.
Yeah. Yeah, thanks. I understand. Mhm.
Okay. Well, I appreciate the question. Yeah, just make sure to check out my videos on YouTube, and
Yeah,
I think you might find something interesting there. Does anybody else have a question or? Go ahead
That's
and
pretty-
raise your hand, and we can. Let's see, Justin Brees. Okay, hold on a second. Go ahead and. Okay, Justin, you there?
Hello.
Yeah, go for it. Yeah, I can hear you.
Oh, hey, how you guys doing?
Good, thanks.
Good. I guess I have a question. If you're looking to start out making initial measurements for electrical apparatus, I'm trying to get a workbench together. What would you guys recommend getting?
What type of when you say electrical apparatus, stuff like that, what type of experiments are you looking to do, Justin?
High potential, high frequency alternating
So
currents,
Tesla.
kind of. Yeah.
So Tesla coils. Well, I mean, the easiest way to answer that is first of all basically to build a Tesla coil. So there are plenty of videos. I mean, I don't know how much you've investigated it already or anything like that, or what your background of experience is. But the best way is to jump in and to start building something, because then you will discover very much along the way what it is, what equipment you need, what parts you need, and you just refine it and take it from there, rather than filling your bench with things that you not necessarily need when you start. Is probably to start simple and work out from there. I mean, there are many places you could build you can get instruction on how to make a Tesla coil. I mean, Aaron, I think one of the presentations last year was on how to make a basic Tesla coil.
Right. And well, actually, I believe I do have a Tesla coil. I purchased a diathermy machine. But I'm trying to get initial measurements coming out of the machine, and I'm wondering,
What type of measurements are you trying to make?
Well, I'm trying to get the voltage, and I'm also trying to get the current.
Okay, I mean, if you have a diathermy machine, so a diathermy machine basically is a simple Tesla coil. So it has a line circuit. So it has the incoming line circuit, which will basically go through to a primary, and then obviously you're going to have a secondary. Now, measuring voltage and currents in the primary is a relatively straightforward thing. I mean, you can do that with a voltmeter and an amp meter. Measuring things in the secondary, that's much more sophisticated and a lot more dangerous as well. You have to be very careful of how you go about measuring things in the secondary. Even with a lot of experience, it's not that easy, and sometimes you have things go wrong. So if you're wanting to measure, say, your input power to it, then you could do that relatively straightforwardly. But if you want to measure your output power, or you want to measure the frequency of oscillation or things like that, then you'll need to set up some basic equipment like some kind of field meter, and you can connect an aerial, for example, to an oscilloscope, because that will pick up the high voltage field that's actually around that diathering machine. So starting along those lines, but I would be very, very wary and careful of trying to connect anything to the secondary of a diathering machine. You're dealing with a spark gap Tesla coil. You're dealing with voltages on a secondary of a diathering machine is going to be at least 50 or 60,000 volts. I mean, low currents, of course, but nonetheless, I mean, that kind of measurement equipment, if that's what you're referring to, and that kind of equipment don't go together very well.
Right. Yeah, that's what I was just trying to get at. Just a basic, introductory measuring equipment that I could use to, get measurements from a diathermy machine that
there are lots of
use.
videos. There are lots of videos on my website on how to, because I enjoy measurement. I mean, I was trained in measurement. I do a lot of measurement equipment. It's one of the things I specialize in. So if you go to my website, aminnovations.com, you'll find all kinds of videos there on making measurements. And that doesn't mean that from time to time you don't blow something up. Isn't that right, Aaron?
So Adrian, you could probably comment on high voltage probes.
Absolutely. So a high voltage probe is a very good thing to have, but you have to be very careful how you use it, because unexpectedly it can suddenly take the heat on a system where something goes wrong. So for example, we had on the hybrid system, we were using this high voltage probe that Aaron had just purchased. I have plenty of them in my lab too. And we had a point basically where the generator stopped oscillating. We didn't expect it to stop. Well, it didn't stop oscillating, but the flame speaker blew out because of their very high modulation. So in other words, we basically went to change a track. The modulation was too high. The new track came in, a new soundtrack came in with very high intensity. It blew the flame out because the oscillator couldn't adjust quick enough. And now where does all that power go? So all that power bounced off the end of the Tesla coil, went all the way back to the generator, bounced off the generator, and then went straight into the measurement equipment. And what Aaron is showing you basically is what's left of a $750 high voltage probe.
Not much.
Oh, here, I gotta look on the screen. Okay.
So, I mean, look, even with
it disintegrated the PCB, literally.
It actually burned. The whole thing burned in a huge plume of smoke.
$700 plume of smoke.
Yeah, $750 just like that. I mean,
Yeah.
I've had that happen 4 times in my lab. I've developed probes that go up to 100 kilovolts now, and you can use them safely on most Tesla situations. But measuring anything high voltage like that is quite difficult. And that system was well within the capability of the probe. So the probe was specified for at least twice what that system was that we were running. But even so, when something unexpected happens, I mean, you're dealing with modes here that we don't fully understand. I mean, we're dealing with transverse modes and longitudinal modes going on in a Tesla coil. That's why it's so important to understand a Tesla transformer is a sophisticated electricity laboratory, and a lot of conventional science electromagnetism doesn't understand what's going on with a Tesla coil. So when you get power going in between those modes, so in other words, you suddenly dump all that energy from a longitudinal mode into a transverse mode, where's that transverse mode going to go? Where does that energy go? It's got to burn up the weakest link. And in this case, it ended up, all the system was built very well, and it ended up all at the doorstep of the high voltage probe. Now, fortunately, the high voltage probe protected the test equipment that we were using to actually measure it. But as Aaron pointed out, I mean, the differential probe was twice the cost of the test equipment. But I mean, at least it wasn't the test equipment as well. So the differential probe did do what it was supposed to do and protect the test equipment. After all, we could have had an expensive spectrum analyzer behind that.
Right.
But we didn't. I mean, so we had an oscilloscope. We had a $350 oscilloscope behind the high voltage probe. The oscilloscope survived because what took the force of the collapse of that longitudinal mode into the transverse was basically the high voltage probe, and the high voltage probe wasn't designed for that kind of eventuality happening. And we were running it fine. I mean, we'd been running the system for over an hour, measuring everything, looking at the results on the oscilloscope. Everything's running fine, and suddenly you have something unexpected happen like that. So you have to be prepared for that kind of thing. And it's not to say don't take measurements, but think very carefully about how you're going to take those measurements and what with, and do it safely, and make sure that you have the budget also to cover the things that go wrong. I mean, I've blown four. I offered this to Aaron at the time, partly in to cheer him up a little bit, was that I've blown 4 of those in my lab over the time, in unexpected ways. You know, it's
Didn't help.
no, I know it didn't at the time. But, I mean, I repaired 3 out of 4 of them. I was hopeful at first to repair Aaron's one, but I mean, it couldn't. It was actually, the whole thing was completely burned.
Right, and that's kind of where I'm at too. When I'm reading all this stuff on eMedia Press, looking at the preliminary equations and stuff, and then trying to take the step into actually using electrical apparatus. I'm trying to get, measurement equipment and stuff, and it's kind of a big step, especially coming from, I'm graduating college here, and there's still, a lot to learn. Until you actually, dip into it, you're not really going to learn anything. And that's just kind of where I'm at right now.
So Justin,
I don't want to be farting around.
Yeah.
But,
So Justin, I'd like to make a comment, because I can speak from somebody who does not have Adrian and Eric's type of experience. And what got me started with looking at how to measure the resonant frequency of these type of coils and that kind of thing is that I do have a small little presentation on eMedia Press called How to Measure the Resonant Frequency of Coils, something like that. And it was a method that I learned from Eric, which is very, very old school, a little toroid transformer with a little bit of wire. And then you have an analog voltmeter, like old multimeter, to put on the voltage range. And then you just take one of these little digital signal generators to feed it in, and you can, depend on how it's configured, you can either look for peaks or dips on the little voltmeter and you look at the frequency that you're putting into the signal generator, and you can tune it to get the highest peak or the lowest dip. And then kind of what that particular coil is tuned for. It's cheap. I mean, $10 for a little toroid ring, a little bit of wire, any analog voltmeter, and then $50 to $100 digital signal generator, and you can actually figure out quite a bit with just that. And then if you want to go, more advanced, and to be able to see things that you won't necessarily see with that method instantly, is the vector network analyzer. But Adrian's presentation last year covered quite a bit of that, and going into the in and outs, and using both methods. I'm just getting my feet wet with the vector network analyzer before Adrian left. He gave me a crash course on how to use it, looking at one of the multi-wave oscillator coils that we manufacture, just to show me kind of how to interpret what's on the screen. That's available as a more advanced tool. He already has, Adrian's given a full presentation on that, but I would definitely encourage you to learn how to do it the old school method, low tech, low budget method, like how Eric showed me. because
You have
anybody
to
can
do
do
that
that, and money's
you
not,
have to do that
an
first
issue.
as well.
Right.
I mean, if you want to grow your knowledge, then you basically start at the beginning, because, in other words, don't rush on to using the network analyzer before you know the basics. You know, otherwise, you know, you just become dependent on this kind of instrumentation, which tells you a lot of things, but also you need to really understand what to do with it.
Right.
So starting simple and with the kind of thing that Aaron's saying really is the way to get your hands dirty with it. But as I said, I mean, there is a lot. I mean, as Aaron referred to, I mean, I specialize in measurement, particularly with things like vector network analyzers and spectrum analyzers and stuff like that. If you're interested in that area, there is an awful lot on my website where I go
Okay.
into that.
Yeah.
Sorry, Justin.
I'll take
go.
a look. Oh,
Yep.
sorry. I was gonna say I'll take a look, but yeah. That's definitely where I'm at now. Because it looks like there are equations, and as long as you can get your initial, measurements, you could validate the equations. But the hard part is actually getting the measurements, it looks like. So that's where I got to put more research in. And
To add on to that, because I believe we've spoken briefly over email before, Justin, but in terms of your diathermy apparatus, probably the rudimentary devices that could be used for, say, frequency measurements would be a signal strength meter, a signal generator, and likely an oscilloscope. Those are probably the most rudimentary devices which could be used for very fundamental analysis of a diathermy unit. Now, in terms of potential measurement on the high end of the unit, that's not necessarily going to be practicable with those types of apparatus. And one thing that I want to point out is that the common misconception where with high frequency, high potential, that you could easily measure the potential of the unit based off the spark length, that does not apply in this type of situation. The typical 30 kilovolt per centimeter rule, which finds itself for DC application, does not lend itself to this high frequency, high potential work.
interesting.
Okay, well, hopefully that answered your question. Anything else before we go to someone else? And we're getting on about 2 hours here, so we'll need to wrap it up here pretty quick.
Oh, nope. That's it. Thank you. I got enough to do.
Okay, appreciate it, Justin. Thank you. Let's see, Mark Uden. Yeah, go ahead and unmute yourself and
Hello, can you hear me?
yeah, just fine.
Yes. All right, great. Thank you very much, family. My name is Mark. I'm from Israel. I'm in Haifa, Israel, and I've been watching Eric Dollar's lectures for about 10 years now. Recently, I've purchased a few of the books and the presentations from eMedia Press. I'm gonna purchase some more, and I've really been enjoying the electromagnetic induction and propagation book. I think the space factor is something quite genius. I've never seen this in any textbooks before, and I think it just thank you, Eric Dollard, for all this work and for sharing this with us, and you, Aaron, for bringing this to us. And I'd like to get to the question. So
You need to pause there, Mark. I think Eric is not there at the moment. If the question is for Eric, he's there now. Eric's back.
Yeah.
So
Yeah, go ahead and repeat that, Mark.
Stolen phrasing. I'm really enjoying the electromagnetic induction and its propagation book, and it has put electricity in such a perfect order for me where you can visualize and understand what is actually going on. And I think the space factor is something amazing. I've never seen this in any textbooks before. And just thank you very much, Eric, for bringing this knowledge to us and for sharing it and making it accessible to everybody. And it's just beautiful. The notes, the equations, the artwork is this. I'm really liking it. And I would like to get to a question that I have. So all of that, I was thinking about the when Eric, you said that about the compounding waves instead of making them to go against each other. And I went and put this together real quick and started playing with it. So this is just a flat coil out of speaker wire, and I have some aluminum foil for a primary. But it turns out I don't even need none of this. What I power this with, and I'm going to get to a question real soon, just so you understand what's happening. I'm using this probe over here from a small digital oscilloscope that I have hacked to be a signal generator. And something I really can't really wrap my head around this, and I would like anybody's input on this. When I take this coil and I put an LED across, just across the outside and the inside, and yes, I have two wires, but I'm just using one, so just the same one. And I put an LED on here, and I hook up this probe with, again, just like this. So just hook it up like this. And I start feeding a signal from the DSO. And at about 3.5 megahertz, it lights up. And the thing it's one wire. There's no transformers like with the cosmic induction generator, where you have the impedance matching transform. None of that. It just comes out of here, and the LED lights, and it's the resonance pretty strong. It lights up kind of bright. And I've tried this. Another thing is I've tried this with all sorts of things. So this went out, and I made other coils, and in the end, I just had wire bunched up like this. Just the wire all bunched up with an LED hooked across it, and again using this one probe from just the just basically from this side of the probe. That's it. No ground, no nothing. And I can light an LED with pretty much just a bunched up wire like this. Can you guys go into this and like maybe just any ideas on what's going on here? And the input voltage.
Any conductor that has a length has a resonant frequency. It doesn't matter whether it's wound or straight out or jumbled up, it's going to have some kind of resonant frequency. The purity of the spectrum, will differ, but harmonics won't end up being where they should be and what have you. But basically, it's just once you find that quarter wave resonant point, you're going to get the high potential that gives you the illumination.
And in the case of
could be a 3,000 mile long power line, and at 60 cycles per second, you're going to get a peak, and 180 cycles a second, you're going to get a peak, and what have you, down to, a very tiny little coil the size of a microbe that might, oscillate at 1 gigacycle.
Right.
Well, Griffin had something to say?
Yeah, it was just in essence. So the pancake coil, or just with any wound coil, regardless of its geometry, it's going to have an intrinsic voltage magnification factor, or just a magnification factor as it's called for short. So this will essentially be characteristic of the coil material, the type of conductor, the number of turns, the geometry, what have you. But say if you're going to be powering such a solenoid with a signal generator, which typically is, say, less than 1/4 of a watt, you're still going to have some type of potential transformation that even something as small as an LED will still be able to illuminate. I've had a colleague who has used a similar signal generator or a source of radio frequency with an ordinary coil and could power to, say, half brilliance a fluorescent tube at a distance of 4 feet away with less than a watt, even less than half a watt of RF power. So it mainly depends on just how the conductor is geometrically arranged to maximize that voltage magnification. But of course, in this case, it's somewhat minimal yet respectable.
Okay, thank you. But also the power comes out of one wire, so it's just basically it's just voltage fluctuating. I'm not connecting the other end. So this is because these probes, right? So here's the ground, so that's minus, ground, neutral, whatever, and there's the that's the probe that's where the signal, the voltage comes out of.
Mark, I
Sorry.
think it's important to understand also that, I mean, with any, just carrying on from what Eric and Griffin have already shared, but ultimately you are dealing with an arrangement of a wire, which what you indicated was not just a straight piece of wire. It's even a bunch, a coil, a bunched up piece of wire and stuff like that is in fact actually a transformer. I mean, you need to consider both the longitudinal and the transverse modes going on, even for your bunch of wire. So, for example, the longitudinal mode is not concerned about, you know, the number of conductors.
I guess I'm sorry. May I interrupt?
Sure.
I'm sorry. I just don't want. I guess my main question here is that how can an LED light up? Because you would need power to light the LED, but how can it get power if only voltage can get from the oscillator into the coil? Because I'm not connecting the ground. There's no electromagnetic circuit. How does that work out? Or like what is happening here? Because there's power in the coil and there's apparently no power coming out of my oscillator.
Well, all your probes and shields and, you know, surface areas, all of that has capacitance. So it doesn't need another conductor. It'll just use the lines of force to close the circuit.
So it'll just close
not very effectively, but nevertheless, you know, it will use, you know, because something has a power cable or, you know, something has some surface area or length, and all of a sudden, you know, you're not dealing with DC and electron flow here. You're dealing with forces and fields. You know, electrons do not flow through a capacitor, and they sure in the hell don't build up on the plates like the physicists want us to believe. That's stupid. If that's all that happened, why are the plates pulled towards each other? It means something's in between. You can run as much as you can run in some big industrial heating application. You can have 5,000 amps flowing through plate to a capacitor, but it's not DC, it's AC. So everything changes. Is what's a conductor doesn't have any meaning anymore.
Okay, so then may I ask a follow-up question?
Mark, let me just, Mark, if I could just add one thing on there, just to clarify something also, because what Eric shared was very important. In this is basically consider in your system now what is happening with the magnetic and the dielectric induction field. So in other words, what is happening in the space around the wire and its configuration and everything like that. It is a complex relationship between those two induction fields, which is leading to the fact that you can light an LED.
Right, and that's the same. I'm thinking along these lines. That's why I'm trying to make sense of it, and that's why I'm trying asking.
I mean,
you
for
guys
example,
about
let me give you an example for an experiment that we did, which is quite an important one. So you take two Tesla transformers and you put them a distance apart from each other. Like, for example, Eric's Colorado Springs demonstration, or the twin pancake coil or something like that. You put a single wire in between the two. Okay, you put a generator on one end and you have a load at the other end. So we can send power along that single wire. We can light the load at the other end. Now, take a piece of that single wire out and replace it with a strand of wire which is no thicker than a human hair. And then you still send, say, 1 kilowatt of power from the generator to the load at the other end. Now,
right, there is a great demonstration.
Exactly.
Right.
There is a specific demonstration for that. And now, in normal terms, if current was flowing through the wire and everything like that, that wire should just act as a fuse.
No, yeah.
Because there's no way it can carry that much on that way, but it doesn't. It doesn't act as a fuse, and that's because the power is conveyed by the dielectric and magnetic induction fields in unison propagating around the outside of the wire, and the wire is acting simply as a waveguide in directing
Right,
those.
absolutely. Yeah.
And moreover, the magnetic and the dielectric induction fields are in phase. So they are spatially in phase and temporally out of phase. So so the longitudinal mode is different in that respect. So therefore, single wire so-called conduction or single wire propagation is quite possible. But nothing is traveling through the wire, in the wire, because it would immediately act as a fuse in that situation.
Right. And that's the kind of thinking that actually got me to making this, is because I was visualizing how all of that propagates around the wire, how it interacts with the next and the next part of the coil. And so I guess I have another follow-up question. This is something I'm gonna try sooner or later. I just been a little busy again. Life happens and stuff. So if I, instead of using a oscillator like this with its battery inside and all of the wires and everything, and like Eric was saying, with all these stray capacitances, what if I just take a 12-volt battery and I make a really simple a MOSFET-based circuit that is just going to make and break a connection, and I make it all self-contained, so there's no power coming out of anything besides the battery, hopefully, and I hook that up and I let it run, and now the negative side of the battery is not connected to the solenoid. It will probably be powering the actual oscillator itself in order to get it to the proper frequency. Will the battery die? There is no actual current. There's no conduction current flowing from the plus and the minus of the battery. There's probably some kind of displacement current going on here, but will it die?
Well, you are still drawing power from the battery, ultimately. A single wire doesn't mean that you are basically creating energy out nothing.
Right.
You are still drawing power, it's just in a different mode.
And I would be interested in how a battery would react to this, because at this point, we're not just using the actual connection, just the connection at the top of the battery. It's basically the whole battery, and all of the contents are going into this interaction with the electrical system that's being powered by one wire. Is that kind of how it works out to be?
If you were switching, others will obviously have more to add. But if you're switching it, then ultimately you are setting up a situation where you have the magnetic and the dielectric induction fields have a relationship around the wire of the system. So therefore, power is conveyed by the relationship between those two fields across the electrical system. If you're not switching it or you're not oscillating, that system will just sit there and do nothing. So in other words, with one end of the battery not being connected in that respect, that battery is just going to be subject to its own internal processes, and it will sit there basically holding whatever charge it has or whatever energy stored that it has, like you would with a capacitor. But if you start switching the system, chopping it or oscillating it, then that's another matter, because now you're changing the relationship between the magnetic and the dielectric induction fields, and then you will get propagation.
Okay.
So now what you're proposing is just connecting this switching transistor to just one terminal of the battery?
Yeah.
Well, nothing will happen. The battery can't engage because in order for DC to work, it has to have a closed circuit.
Mm-hmm.
No. What maybe I didn't make it completely clear. Instead of using this kind of oscillator, I'm using the battery to power my coil. So now what I'm doing is I'm basically making a break-in connection to the plus terminal of the battery with my coil, just kind of like
Where does the negative terminal of the battery go?
It doesn't. I'm not connecting to it.
Well, then you won't be able to draw any energy out of the battery. Now,
Right, but then
let me finish. But if you build this thing and connect to one terminal of the battery and it powers, then you've cracked open a new situation. So I'm not going to dissuade you from doing it, but any electrician, electrical engineer, or anybody would tell you, well, you're not going to get anywhere with that, but try it. Now, if that thing lights up with only one terminal of the battery, I would be flabbergasted, and then we really have to start rethinking everything. So maybe that's what you need to do. But
Yeah,
normally, the switching transistor has to work in a closed loop, your primary winding, and excite the secondary. You do not need the oscillator in the silly phone or whatever that thing was. You just basically. But the thing is, you have to switch the transistor at the rate which the coil wants to resonate. Otherwise, your effects will be feeble.
right.
But nevertheless, if you just, close the circuit, let the magnetism build up and then break it so it's got to escape, you'll get an interesting oscillatory transient on your oscilloscope that will reveal much more about the nature of the coil than just trying to operate it on a particular mode that lights up. Because then you'll see all the modes interact with each other. That's the advantage of using the disruptive discharge or spark gap or switch method over the continuous wave oscillator, because when we work with the continuous wave oscillator here, it will not operate in multiple modes. So I thought that it had the possibility of doing that, but when we actually got into the matter, it will not oscillate in multiple modes. So essentially, there's very little reason not to just use the forced signal generator rather than a self-oscillating generator, other than the self-oscillating generator is simpler. So basically, if you want to see the character of the coil, it's like a bell. You can hit a bell and you can hit it once, and all of its various modes will present themselves. But you can also have a loudspeaker pointed at the bell and pick one of those modes out, and the thing will ring like crazy. But you won't see all the interaction between the modes. You see what I'm saying?
Right.
I got into this in my Colorado Springs presentation. I got into incredible detail exactly how all this stuff works in these coils. I mean, I laid it out pretty clearly.
Is it available on eMedia Press?
Aaron would have to.
Yes, the Colorado. Yeah, if you go to emediapress.com and then you go to the there's a search bar at the top right, the search field for products. And if you just type in Colorado Springs, it'll come right up. I think that was a 29. I think it was a 2019 conference.
Okay, great. I think that's some of the presentations I didn't get last time. I just ran out of cash, but
Okay.
I'm getting them now again. Thank you very much. That was quite enlightening. Thank you. Thank you so much.
Okay, thanks, Mark. Okay, I guess it's about 2 hours, 17 minutes. We can probably wrap it up. Hopefully everybody can get their conference tickets, come meet us in person here at the underground shop here in Spokane, Washington. It's coming up in July. And again, any donations to EPD Laboratories Inc. will help to continue the progress of what Eric has going on down in Nevada. And again, the expenditures did increase quite a bit, especially on the building insurance. It's like $2,000 a year just for that. And let's see, any final words, Griffin or Adrian, or I know that I think Bruce Gavin is on the call. Okay, maybe not anymore. Just going to see if he had anything to throw in. Otherwise, any final comments, Eric or Adrian or Griffin?
Yeah, well, I got one comment is it's rather disappointing that after, all this effort and what have you, is really not enough money came in for the upcoming work episode. That's very disappointing. So I'll have to expend all my savings to push this thing through, because I guess there's just really not that much interest in it, which is very discouraging, because where's the money going to come from to really develop a project like this if there's such little interest? It kind of left me in a bummer. And then, as you pointed out, what we're doing here is literally a money vacuum. You might as well just, go into the bank with an industrial vacuum cleaner and suck it dry. And then $750 disappears in a black cloud of smoke rising to the ceiling and blows away in the wind.
Yeah, it's a challenge. So, but nevertheless, we made amazing progress. The audio modulator bay is working, doing the hybrid with the Adrian's equipment and the RF power supply. And depending on what the timeline looks like after the conference, hopefully we can get close to completion on that and take it to even another level. And that's what's going to be coming. And that might be conference next year if the world holds together, and we can do that.
Well, we're planning to do the Colorado Springs development after the conference, so there is a plan for that if we can.
Yeah, that'll basically be another presentation in a recorded version.
Absolutely.
Yeah, so basically part 2 to the 2019 presentation.
Yeah,
Right.
it'll be a sequel.
Right. Okay, well, I guess everybody, thanks for being on the call. I'll get this up on YouTube when I can. Probably after, I'll wait till after Eric leaves, because I'm pretty much going nonstop from the time I crawl out of bed until I pass out at night, 7 days a week. And but that's kind of what it takes. So, and then the call from 3 weeks ago, I'll get that up on YouTube first, just so that they're in sequence. And Adrian has a website also. It's am-innovations.com. And Griffin's website is griffingbrok.com. There's also donate links on their website as well. There's a lot of content on there that's directly related to pretty much everything that we discussed on this call. And then emediapress.com and energyscienceconference.com. And then there's Eric's website, ericpdollar.com. And I guess until next time, let's see what 3 weeks from today is going to be 27th of May. So do you want to say we'll do the next call in 3 weeks then?
Yeah.
27th of May should be when we go down to Tonopah.
Okay, so you can broadcast some progress of what you're doing down there.
Yeah, likely.
And everything. So yeah, that'd be great. So okay, well, we'll see y'all on the call on the 27th. Have a good weekend, and we'll talk to you all later.
Right. Thank you, Aaron.
Okay, thanks everybody. Take care.